the DFE. Okay, thanks.
The next question is, I will need to move into a new office room, which was assigned during the pandemic, from where I was physically using before COVID. Do I need to follow specific actions for that? I'm not sure I understand this question. I know at this point, logistics isn't doing any moves for like getting your personal items from one location to another. In terms of it's just, you know, I'm moving my person to a different office that's already been set up for me. There shouldn't be any special actions needed to be taken. You know, as long as that, you know, that.
Hi, Hannah.
Hello.
I'm not sure who was just talking there, but I'm glad to see you.
It's good to see you too. All good.
How's everything going?
It's going okay. We're trucking along with this project. We have a draft that we're just trading back and forth now. So it's in the home stretch, which is nice. So everything else is all right. I think I'm tired of being at home, but you know.
I know. Are you in Colorado or are you?
I am for now. I will be going to Wisconsin for 3 weeks starting October 7th. So
Okay.
that will be good. So Angel and I will see each other then, and then I'll be back, and I don't move until the end of March. So
I don't know where you.
oh, sorry, I forget that you. Yeah, okay.
Once in a while, yeah.
I'm moving to Wisconsin at the end of March, so I have a faculty position in the Department of Atmospheric and Oceanic Sciences.
Oh, that's
there.
awesome!
So, yeah,
Congratulations.
Yeah. So I don't start until next fall, but my partner's there already, and so
Right.
he's started in their department, and so yeah, a little wild.
That's awesome. I'm so happy to hear that.
Thank you. Yeah, it'd be nice to be in the same place.
Yeah. Can I add that to your introduction?
Mm-hmm. Of course.
If you're just to let people know, that's awesome.
Of course. Yeah. So. All good stuff. So yeah, I will finish my postdoc remotely. I'll probably take some time off. I haven't decided yet how long that will be, but maybe take part of the summer off and then start.
Yeah.
So do that.
And then you're going to start in the like a year from now, like next fall.
Yeah. Mm-hmm. I figured it would just be better that way. Take time to finish out my work here and enjoy my time here in the sun and the not so frigid temperatures.
Yeah.
So,
yeah, like one
doing?
Colorado summer, or I don't know, whatever you want to do, traveling.
Right, exactly. So,
do you live in Boulder?
I live in Gun Barrel, so yes-ish, but not Boulder proper, I suppose. Mm-hmm. So yeah, I'm up Highway 119 a little bit. So
yeah, we just moved to Longmont.
Oh wow, okay, yeah.
So we were renting in Boulder for about 3 years.
Yeah.
But we just bought a house in Longmont. So
oh, congratulations! That's exciting. Yeah. I feel like Longmont seems to be the place to go for things that are like vaguely affordable.
Exactly.
So.
Yeah, exactly. Or Gun Barrel's not too bad either. But we were basically looking, kind of in this area around Boulder, but not actually in Boulder because there wasn't anything. Right.
You can spend $800,000 on something that's falling apart. It's like Seattle, man. Like,
okay. Tracy's asking me. Screen looks good. Oh, that makes sense why we heard her talking before. So Tracy shares this like intro slide that you can probably see.
Yeah.
And then we won't start until at least right at 11 because people like slowly trickle in. Mm-hmm. And then I'll start introducing you, and then while I'm doing that, she'll stop sharing, and then
then I can share my screen.
Start sharing whenever you want. Yeah.
Perfect. Okay. That sounds good to me.
And yeah, usually we do like, 10 minutes or so at the end for Q&A. But yeah, I mean, it's up to you how long you want to go.
Yeah, that's totally fine. Either ways chill. I can always talk to people outside of it too, so.
And we're also streaming this on YouTube for people who can't.
I saw that. I was like, oh, hey.
For people who can't join Zoom. And then I think that's how they share the recording after, is like the YouTube link. So
okay. That's cool.
Yeah, I know with all these virtual things, there's going to be a lot more like recordings of all of our talks and everything.
Right, which is cool, I think, for the most part. Except sometimes you're like, oh, when you say something dumb, you're like, I wish that recording would go away.
And then it's just preserved in the
right. Right there. But I think it does make everything far more accessible. Yeah. How's everything going for you?
Good. Yeah. I mean, the big thing was just move and getting settled.
Yeah. When did you move?
About a month ago.
Oh, wow. Okay. Right. So it's like, this just happened. This is like pretty hot off the presses. That's so exciting though. It's nice to like have that, feel like I have a home.
It is. And it's like much better for work from home for both of us. So,
right.
So that helps.
Yeah, definitely encouraging. I know I'm okay now working from home. It took me a while to adjust, but like I think the issue is now that it's so long term, it's like I would really upgrade my situation because my, I have some crappy desk that I had from like my college days, It's just, I bought at Target and I had to buy a new chair for the same reason, things that like you have, but you never actually expected to use on a regular basis.
Yeah, at least not use this much for sure.
Right. So it was really funny. But I mean, I'm getting a little tired of my cramped quarters in that sense, but it works, I guess. Well enough, I'm making progress, so.
All right, why don't we get started? Are you okay to go?
Sounds good to me.
Cool. So welcome everyone. Thanks for joining. Today, I'm very happy to introduce Dr. Hannah Zanowski as our speaker. Dr. Zanowski is a postdoctoral research associate at the Institute of Arctic and Alpine Research and the University of Colorado Boulder. She received her bachelor's in physics and mathematics from the University of Arizona in 2011, and her master's and PhD from Princeton University in atmospheric and oceanic sciences in 2016. After a postdoc at the Joint Institute for the Study of Atmosphere and Ocean, which is at the University of Washington, she joined INSTAR and CU in 2019. And just today I learned that she'll be joining the University of Wisconsin as an assistant professor in atmospheric sciences in fall 2021. So that's very exciting. Congrats, Hannah. Her research focuses on polar oceanography. And one thing that I really loved from her website is that it says, if there's one thing you should know about her, it's that she rocks oceanography from pole to pole. And so today she's going to talk to us about Arctic freshwater storage and export in CMIP6 models. Take it away, Hannah.
Awesome. Thank you, Katie. I appreciate it. And yes, I do rock oceanography from pole to pole. I forgot that is on my website. So today we'll be in the North Polar region, but my background is actually largely Antarctic. So pretty cool stuff. So again, like Katie said, I'll be talking to you today about Arctic freshwater storage and export in CMIP6 models. And so this is some work that I've been doing with Alex Jan here at the Institute of Arctic and Alpine Research in the Department of Atmospheric and Oceanic Sciences at CU Boulder, and then with Marika Holland as well up at the National Center for Atmospheric Research, as I'm sure many of you on this call know. So I like to get started by sort of describing the Arctic from a very rigorous scientific perspective, which is that really the Arctic is just a whole lot of ice and ocean and rivers. Now, I understand that if you're a biologist or an ecologist, that's a pretty horribly blasphemous way to describe the Arctic. But since I am a physical oceanographer by training, the ice and the ocean and to some degree the riverine inputs are really the things that I care about the most. So I have a figure over here on the left from Moon et al. 2019. This is kind of just describing the frozen parts of the Arctic. Got various things like land ice, or really the ice sheets over Greenland. So the Greenland ice sheet in the yellow colors here. You also have frozen Arctic Ocean, which is just sea ice in the white colors here. And then of course, the regions of the permafrost in these sort of light pinkish colors all over northern North America and northern Asia as well. So the Arctic also hosts a really complex ocean circulation. It's a figure from the Woods Hole Oceanographic Institute that kind of just is a schematic of all of the different transports or flow in and out of the Arctic Ocean, which is sort of the central region here. So you've got sort of exchanges with the Pacific Ocean through the Bering Strait. You've got flow into the Arctic from that region. As well as sort of flow out on the other side through to the east of Greenland, which is through Fram Strait, and then in these sort of various passageways through the Canadian Arctic archipelago, as well as outflow and exchange into the North Atlantic in this region. You also have sort of, again, further exchange with the North Atlantic on this part of the Arctic here, which is with the North Atlantic Current, which is inflowing partly through Fram Strait and also partly through the Barents Sea opening. And then just a pretty intense circulation within the central Arctic basin itself, as really is the Arctic Ocean. For the most part, the thing you kind of need to understand here is that you've got the Beaufort Gyre within this region, which is this sort of circulation right here. So that's sort of the main gyre circulation within the ocean, within the Arctic Ocean. And then of course, a lot of exchange throughout as well. That's sort of how I like to think about the Arctic, as this sort of frozen aspect, and then a sort of ocean circulation and exchange within these other ocean basins as well. So we typically think of the Arctic as a frozen place, but unfortunately the rate at which that is becoming untrue is kind of disturbing. So the Arctic is really one of the fastest changing regions on the planet. There are a lot of different ways in which this is occurring, but again, I'm mostly going to focus on the ice and ocean components of this system because that's largely what we're going to be talking about, or what I'm going to be talking about today. So sea ice, of course, in the Arctic is majorly declining. What I have here is sea ice extent from 1979 to 2020 from the National Snow and Ice Data Center. So this is extent in millions of square kilometers on the y-axis and then time on the x-axis. And this is the average monthly Arctic sea ice extent from, again, June 1979 to 2020. That's what the black line is. So you're seeing this sort of interannual variability. But what the blue line there is showing is basically this very strong negative trend in sea ice extent in the Arctic over this few decade period. So the sea ice is certainly declining. And at the same time, though, the Greenland ice sheet is melting. And so this is a figure from the IMBY team. This is their 2020 paper that just came out in Nature earlier this year. And I have this quote from them here, which kind of describes the magnitude of the situation, which is that the Greenland ice sheet has lost about 3,900 gigatons of ice to the ocean since 1992. And so that's what this figure is. It's the mass change from Greenland. On the left y-axis here, that's the actual decline in mass change. And then on the right y-axis is the sea level contribution in millimeters. And then you're going from 1980 to 2020. on the x-axis. So what you see here is that there's sort of declines from changes in the surface mass balance, as well as changes in the dynamics, which are that teal color. But overall, the total ice sort of, or mass loss, is sort of described by that darkest blue line with the error bars on it here. And what you're seeing is basically from about 2000 on, where you see this really, really strong decline in the mass balance from the Greenland ice sheet. So again, major melting of the Greenland ice sheet, as well as declines in sea ice. So there's also a lot of other ways in which the Arctic is changing. For example, on the left is the May snow cover anomaly. This is from the NOAA Arctic report card, which basically is just a really great description of all the ways in which the Arctic is very rapidly changing. And so this is a sort of, the figure here is from about 1970 to 2020, sort of showing you basically the declines in snow cover extent over the Eurasian Arctic in red and the North American Arctic in black here. So again, you have this sort of subtle negative trend over that time period. So again, overall, the snow cover extent is decreasing. At the same time, you're seeing sort of increases in the permafrost temperatures. And if you remember from that very first figure, there's a huge swaths of the Arctic are covered, have permafrost within them. And so sort of you get these changes in this permafrost, so the temperature is increasing and basically they're melting. So again, this is, again, sort of time rate of change. This is from 28 to 2016. And then you can also kind of look at river discharge as well over. This is the scale for this is roughly like 1935 to 2020. You've got Eurasian river discharge on the y-axis on the left in the red, and then in the right, that's North American river discharge in the blue. But what you kind of see from both of these things, though, is that you got this sort of subtle increase in riverine discharge over that time period. So sort of increase in the amount of river that discharge that's dumping sort of into the Arctic as well. So you got increasing river discharge during that period. So you can kind of think about the ice, the components, but the Arctic Ocean is changing too. So this figure on the left is the linear trend in degrees C per year of the sea surface temperature from 1982 to 2019. This is from Timmermans and Ladd, also from the glorious NOAA Arctic report card. And so what this is showing you here, again, are the trends in SST. This is in August of that period. So the white is actually the sea ice itself in that time period, the average of that. And then the colors, of course, are the temperature, and then this darker gray color are areas that are not statistically significant in the actual Arctic Ocean. And so what you're seeing is for most of this area, you have these strong statistically significant and positive trends in sea surface temperature in the Arctic surface ocean, which is basically just saying that that area is warming up significantly. And at the same time, though, you're also getting changes to the circulation itself. And so one example of this, and I'm not going to go into a ton of detail here, is this paper from Armitage et al. In 2020. It also came out earlier this year, which is basically describing how when you lose sea ice or you melt sea ice, it gets stored in the Beaufort Gyre, and that leads to sort of a spin up of the gyre. And in response to that, you have to enhance the eddy activity in that region to sort of spin down the gyre to keep everything sort of in steady state, if you will, to kind of think about it like that. So the eddies are sort of responding to these changes in sea ice loss. Now it's also related to sort of the wind-driven changes as well. But the idea is that, again, you're changing the circulation within this region and sort of changing what is happening within the Arctic Ocean as a result of those changes. And so there's a ton of papers on how the Beaufort Gyre has changed, how it's currently changing, and how it will change. But again, not going to kind of talk too much about that today. So all of the stuff that I've basically showed you so far, these examples of how the Arctic is changing, impact what I call what is known as freshwater within the Arctic. And freshwater, for our purposes, is literally water that doesn't have any or very little salinity, or water, when you're thinking about freshwater in the ocean, it's water that's below a certain reference salinity. But in either case, what I have here is a schematic on the left that basically describes the Arctic freshwater system. And so this is basically just showing you how all the different ways in which freshwater is sort of cycled in and out of the Arctic region itself. So you've got things like atmospheric transport, which brings sort of moisture into the Arctic polar region here. You've got exchanges sort of with the atmosphere and the ocean and the sea ice through precipitation and evaporation processes. You have riverine inputs like that we talked about before. So you've got rivers basically dumping fresh water into the Arctic Ocean, which really impacts sort of the stratification. And then you also have transports and at the ocean, between sort of the Arctic Ocean and then the North Atlantic or the Pacific Ocean, like we showed before. So you've got ocean transports in and out in these black lines. And then, of course, since you have sea ice in the Arctic, a lot of that actually ends up getting fluxed in and out of these various straits here. Especially around Greenland. So you're getting ice in and out of that region as well. And ice is largely fresh too, or sea ice is largely fresh as well. So a lot of different ways sort of that you're exchanging within these regions. And of course, what that means is that the fate of the Arctic freshwater doesn't just matter for the Arctic. And this is kind of an important point to kind of take home is that, well, Arctic freshwater, for example, impacts North Atlantic deep water formation. And so what you see here, like I just described, is that you have a lot of these freshwater fluxes in and out of the Arctic through sort of various straits in the Canadian Arctic archipelago, as well as the Barents Sea and the Fram Strait, these ice and ocean fluxes. And what's happening is you're actually exchanging with the North Atlantic, which is a little bit further south here in this figure. And as a result of that, though, if you bring a bunch of freshwater out into the North Atlantic, that of course is going to impact convection in the region. It's going to impact how much of that dense water is formed. And that's going to sort of lead to lots of different sort of changes as well. Now, another way that can happen are these things called great salinity anomalies. So back to the Beaufort Gyre, that Beaufort Gyre typically stores a bunch of fresh water, but there are times where that sort of breaks down and it releases all of that fresh water, and then you actually get a ton of fresh water flowing through, again, further flowing through these straits, once again impacting the salinity, if you will, of the North Atlantic for a time period. And what that does then is that eventually slows or changes the AMOC, and of course, then that relates to global climate. So what happens in the Arctic, of course, doesn't just stay in the Arctic itself. So this is kind of why we need to understand what's happening in this system. So naturally, because of that importance and because the Arctic is just a really interesting place, scientists have tried to sort of quantify or understand the Arctic freshwater budget. And so the freshwater budget itself is basically just a sort of a description of, again, just keeping track of all of the different freshwater within the Arctic and how it's leaving and entering the Arctic, what comes in, what comes out, a typical sort of balance situation here. And so this schematic on the left here is from Serez et al. 2006. This is sort of more or less the 1980 to 2000 Arctic Basin freshwater budget. And so you don't have to focus too much on the sort of details here of all of these different arrows, but largely what this is kind of just describing is basically there are these sort of reservoirs of fresh water in the ocean. So that's storage, if you will. There's various storage in the land, the atmosphere, and then sort of exchanges between these reservoirs of that fresh water within there as well. And so there's a ton of inflow and outflow, especially for the ocean component of it. Like I said, we saw sort of flow through these various straits, which are sort of described on this map that I have over here. And what you're seeing from these, and one thing that I do want to point out that I think is pretty nifty is actually if you look at the water, the flow through the Canadian Arctic archipelago, which again are these really, really small sort of straits in this complex sort of islands situation happening over here and next to Greenland and North America. And we actually have a pretty strong outflow through the Canadian Arctic archipelago. So even though you have these kind of small things that maybe seem inconsequential, they're really not. So Hayne et al. In 2015 kind of did an update to this freshwater budget, where once again, they looked at the 1980-2000 period. They also looked at sort of changes from 2000 to 2010. That's kind of what this table is showing you here. And don't worry if you can't see the numbers too well. You don't need to memorize everything. I'll be comparing to observations later. But they also kind of looked at these sort of changes, how these changes might occur over the 21st century, looking in climate models as well. So trying to understand the freshwater budget has really been the focus of some part of Arctic science for a pretty long time. Now, For my purposes, though, I like to take all of those schematics and put them into this very, very, very simplified version of what's happening here, where you just have exchanges between the river, the atmosphere, and then the sea ice and the ocean component of the system. And then sort of just the fluxes through these various straits within these regions. But for my purposes today, I'm going to kind of ignore the atmosphere and the riverine inputs. And I'm sorry for my atmospheric people on the call. It is what it is. So I'm going to focus on the sea ice and ocean component. So the storage, we're just going to be looking at the solid storage in the sea ice and then the liquid storage in the ocean. And then sort of our inputs or imports and exports, or just the transports through these various straits within these regions. So naturally, since I'm a modeler, this talk has to at least discuss a little bit about modeling studies. And so there's been a ton of modeling studies to understand sort of freshwater within the Arctic, how it's changing, all of that good stuff. But since I'm going to be doing a couple model intercomparison for the CMIP6 here, I'm just going to focus a couple of things, so CMIP3 and then CMIP5 models. And so just to kind of set the stage for you in terms of what we're going to talk about. So what I have here from Holland et al. 2007, this is freshwater storage and trends in CMIP3. On the left there is the model liquid transport change. This is sort of mid-21st century minus mid-20th century. So you've got transport through these various straits. So this is Fram Strait, Barents Sea, and the Bering Strait. You don't worry too much about where those are at the moment, but what you have then on the x-axis is just the different models in this study that Marika did. Marika and co-authors. And so over here on the right, these figures are just the model solid and liquid freshwater storage. This is just a mean from 1990 to 1999. And so again, the storage values are on the y-axis and then the models are on the x-axis. You have liquid freshwater storage. So again, the freshwater in the ocean, and then the solid freshwater storage, which is the freshwater storage more or less in the sea ice. And then this dashed horizontal line here is basically the observations over that same time period. So when you look at all of these figures, basically what you take away from this is that the models really disagree on what is happening in terms of the transport changes, but also like what is happening for the solid and the liquid freshwater storage. So in the transport case, you've got models disagreeing on the sign of the change of those the transport itself. You've got major differences in magnitude of those fluxes. And then more or less the same sort of story in terms of the solid and liquid freshwater storage, sort of very, very strong differences in values, and then only a couple of models kind of coming close to observations. So main takeaway is that the models in CMIP3 really disagreed with each other. And that another important point, though, is not all of the models in the CMIP3 class of models actually had the Barrow and Nares Straits open in the Canadian Arctic archipelago. And like we saw before, that actually is a significant amount of freshwater exchange with the North Atlantic Ocean. And so not having that kind of forces everything to kind of go through the eastern or Fram Strait route through here. So these models at the time were just too low resolution to be able to pull that off. Now, fast forward a little bit to CMIP5, which is the previous generation of CMIP models. This is now from Xu et al. 2018. This is the multi-model mean projected freshening trend. This is from 1950 to 2100. It's in meters per decade as the unit. And so they average a ton of models in this study and kind of look at what the freshening over this 150-year period in 4 of these different representative concentration pathway or RCP scenarios. So these are just the future forcing scenarios in the CMIP5. And so they're basically just these numbers at the end of these RCPs are just describing the radiative forcing anomaly at the end of the 21st century. So RCP 2.6 is 2.6 watts per meter squared radiative forcing anomaly at that time period. And then 8.5 would be the much stronger version of that. So they're kind of just showing you how things freshen over that time period in these 4 different sort of future scenarios. And kind of what you're getting from this basically is that you see this really, really strong freshening. That's the strongest in RCP 8.5 versus RCP 2.6, especially sort of in the Beaufort Gyre region. Now, of course, when we do multi-model means, we end up sort of averaging, of course, over a lot of different changes across individual models. And so even though the multi-model mean might actually say, hey, this is an idea of what all the models are doing, it's important just to keep in mind that individual models sort of end up showing just not only magnitudes of changes, but sort of the spatial structure of the changes can be quite different. So this is, again, from Hayne et al. 2015. This is a single model liquid freshwater content change. So it's not a trend anymore. It's just like an absolute change. This is from the end of the 21st century minus the beginning of the 21st century. And just one of these scenarios, so RCP 4.5. And these are just two different models that sort of participated in this Xu et al. Study as well, or at least the same class of model. And what you kind of see from this is the change in liquid freshwater content described by these colors here in the Arctic is really quite different. The magnitude is different in GFDL versus the MPI model. But also the sort of spatial structure of that, where MPI is basically showing a stronger freshwater content change in the central Arctic, whereas the GFDL CM3 is basically saying, no, this is going to largely be focused in sort of this Beaufort-Gyre region, sort of north of Alaska and northern North America. So again, when you sort of do multi-model means, and I will be doing multi-model means today because it's sort of one of the best ways to sort of present the information for many different climate models, it's just a good idea to keep in mind that sometimes these models behave quite differently under the surface. And so we'll kind of look at both of those things today. So last, what I want to show you here is this also from Xu et al. 2018. This is kind of looking at how the freshwater fluxes through the various straits change in the CMIP6 model. So again, this is your handy dandy map of the names of all of these straits. So just keep this. This will typically be here through most of the talk. So if you don't know where something is, just refer to it. So get used to seeing it. And so what these figures are the freshwater flux anomalies over time relative to 1950 all the way to 2100. And so we're looking at a couple of different straits in these regions, and I'm just comparing two different scenarios here. So RCP 2.6, that sort of low radiative forcing scenario, and then RCP 8.5 on the bottom panels, which is that high radiative forcing scenarios. So positive anomalies basically mean Arctic freshening in this case. And so I'm showing a few different straits here. So there's a Barents Sea opening, which is this over here. There's the Fram Strait solid and liquid fluxes. So there's a lot of ice and sort of ocean transport that comes through Fram Strait, and then the Davis Strait liquid fluxes only. And so this is, again, from Xu et al. Basically showing you that sort of you get these sort of strong freshening or increases in freshwater fluxes through the Barents Sea opening over the time period, whereas the liquid fluxes in Fram Strait actually lead to increased export of freshwater out of the Arctic, sort of major changes in the Davis Strait and then the Fram Strait solid fluxes as well. So we kind of have an idea of how all of these sort of fluxes have changed according to the multi-model means in the CMIP5 models, thanks to this study. So for me, my overarching research question then is, what is the state of Arctic freshwater storage and fluxes in CMIP6 models, and how is this going to change in the future? So my one method slide here, my overall goal is to characterize the CMIP6 model Arctic freshwater storage and export during the end of the 20th and the 21st centuries. And to do that, I'm going to compare all the models from CMIP6 that have at least 10 ensemble members for their historical simulation. There's typically fewer for those future forcing scenarios, but as a cutoff, we want to say, because we want to kind of look at model internal variability as well, we want to have those ensemble members as well. At the same time, I also need these models to provide me the relevant variables on ESGF. So if I didn't have all of the things available to compute the fluxes and the storage, that knocked off maybe a couple models. And what this leads me to, based on these criteria, it's just a total of 7 models that we're going to be looking at today. And so that will kind of help all of our sanity, if you will, when comparing across many CMIP6 models, because there's quite a large number of them. 7 is a pretty small chunk of them, but these are the 7 that sort of, again, adhere to these criteria. And so these 7 models are nominally 1 degree resolution in their ocean and sea ice. Now 1 degree, again, is, like I said, is just nominally so. It doesn't mean that there can't be variations in their sort of meridional resolution or their zonal resolution, but on average it's something close to 1 degree, but they can be above or below this as well. So I'm going to look at 3 different experiments for simulations from CMIP6. This is going to be the historical simulation. So this is actually a run that's from 1850 to 2015. Sort of forced with sort of historical changes or sort of historical forcing values. But mostly what I'm going to focus on is this 1980 to 2000 period and looking at sort of averages over that period, unless I'm looking at time series. And then I'm also going to look at 2 shared socioeconomic pathways. These are future forcing scenarios. These are the SSPs are basically the CMIP5 or the CMIP6 or analog to the CMIP5 RCPs. So a lot of jargon here, but basically they sort of describe the same thing. I'm going to be looking at a low radiative forcing scenario. So this is again that 2.6 there at the end is the 2.6 watts per meter squared radiative forcing anomaly at the end of the 21st century. And then SSP 5-8.5, that 8.5 means that we're having an 8.5 watts per meter squared radiative forcing anomaly at the end of the 21st century. So sort of a low radiative forcing or low warming scenario versus a much higher scenario. And these, I'm just picking 2 of these to sort of bracket sort of what changes we might expect to see over these periods. And when I look at the SSPs, typically I'm going to be looking at the time period, the last sort of 2 decades of these simulations, so from 2080 to 2100. And so I'm going to do a lot of comparison then to the 1980 to 2000 historical period as well. So I just want to first off then explain the freshwater storage and the transport or the flux definitions here that I'm using throughout this study to sort of compute all of these values. So for my purposes, freshwater storage is just the volume of freshwater in the Arctic. And how you compute freshwater in the ocean in this case, and at least the way that I'm computing is basically just what is the salinity relative of the water relative to some reference salinity. In this case, it's 34.8. And this value is chosen simply because it is comparable to previous observational studies as well as previous modeling studies. So there is a dependence on this reference salinity. But I'm not going to kind of talk too much about that here. But basically, like I said, when we think about freshwater storage, it casts all of our sort of freshwater changes as changes in sort of salinity. And so what I do is I just add up this sort of the volume of this sort of salinity, this freshwater term in the Arctic Ocean. So dA here is our horizontal or our surface area. That's just dx times dy. And then dz is sort of the vertical depth. Or excuse me, just the vertical component or the depth. And in this case, to keep this, this quantity positive definite, we're only going to integrate, in the case of the ocean, down to this, this reference salinity isohaline. So that surface of constant salinity within the Arctic Ocean. And everything else below that is sort of ignored in terms of the volume or storage contribution. And so for my purposes, volume, or this storage, my Arctic domain that I'm computing this over is defined by these 4 straits. So the Bering Strait, the Davis Strait, the Fram Strait, and the Barents Sea opening. So this is my storage domain. At the same time, transport are calculated very similarly. And in this case, transport is just the volume fluxes in and out of the Arctic through these various passageways. So instead, we're looking at if that sort of reference or that salinity term, and now you're just multiplying it by a velocity term to get this flux. So dA in this case is now a vertical section. So either dx or dz or dy or dz, just sort of depending on the orientation of this strait. And so it's our typical definition of just, okay, are things coming in or out of the Arctic in terms of this freshwater? I mean, in this case, we are integrating over the full water column for the transports. And then I add a couple of different straits. In addition to these 4, we're also going to be looking at the Barrow Strait transports and the Narrow Strait transports as well. So 6 different straits that we'll kind of be looking at today. So I do want to show you first off sort of what these models kind of look like spatially in terms of their sea ice concentration in this case. And this is just kind of just help you set the stage and understand what you're going to be seeing in some of the storage values that I may be showing you next. So this is the model ensemble mean sea ice concentration. In this case, an ensemble mean is the mean of each model's ensemble members. There are at least 10 again for each of these models. There are sometimes more. So this is sea ice concentration in the blue colors here. We have our handy dandy Arctic map to keep us oriented. So these are the 7 different models that are in use in this study. And then these yellow lines here are the 15% sea ice concentration contour. This is everything is average 1980 to 2000. This is historical sea ice concentration. And then these orange and red lines are showing you that same 15% sea ice concentration, but for the end of the century for those 2 SSPs. So the orange line is SSP 1-2.6, and that sort of darker orange or red line is the 15% sea ice concentration contour for our SSP 5-8.5. Again, these are at average 2080 to 2100. And this is just to give you an idea of how that sea ice concentration has changed over that time period. Now, first off, though, I want you to just kind of look at these historical simulations. And what I have on the right here is the NSIDC mean sea ice concentration from 1980 to 2000 with that same sort of 15% sea ice concentration contour. So that you can kind of compare across models. Now, it does actually take some time to stare at these to recognize that there actually are quite serious variations between these different models and observations. But one thing I do want to point out here is that in observations, you typically have a lot less ice in the the Barents Sea than you do in a lot of these models. Now, in the historical period, I tend to see, kind of 2 classes of models in these with these sea ice concentrations, where you've got a couple models like CAN-ESM5 up here, and then the UK-ESM model, which have pretty large or high values of the sea ice concentration or ice concentration close to 100%. Over most of their central Arctic region, whereas if you compare that to the MPI model, for example, over here, you have much lower sea ice concentrations within that region. And then when you look at these changes, again, largely what you see is that at least for SSP 5-8.5, which is that darkest sort of colored line here, so that red line or that orange line, for models like CAN-ESM5, IPSL CM6ALR, and UK-ESM again, you actually have a pretty much an ice-free central Arctic within those models, but within the remaining models like the CESM2, and then MPI, MIROC, CNRM, those models at least still have ice within their central Arctic regions at the end of the 21st century in this very high radiative forcing scenario. So you're seeing sort of pretty major changes in the states of these models and sort of pretty different variations across them in terms of their mean state in that historical period. And so what this does then, and of course leads to changes in their freshwater storage. So this now, what I'm showing you is a sort of box and whisker plots of the spread in model freshwater storage. This is historical storage. This is from 1980 to 2000, those averages again. So I've got the 7 models here on the x-axis, and then the value of the storage the models are on the y-axis, the storage is on the x-axis here. And so freshwater storage is in cubic kilometers. Do note that there's about a factor of 10 difference between the solid and liquid freshwater storage. So when you're kind of comparing across these, be a little careful there. But what each of these box and whisker plots represents is sort of the mean of those on the model. For each model, it's the mean of the ensemble members and then the spread of those ensemble members' storage for each of these values. The vertical magenta line, this dashed line here, are observations from Hain et al. 2015. So this is kind of giving the idea of how each of these models are doing in comparison to observations. So largely what you get from this is that the models are really different. You've got pretty major variations in their solid storage, some very high values of solid storage in the UK-ESM model. Some models get a little bit closer where they have at least one ensemble member coming somewhat near, or their spreads are somewhat nearer or closer to observations. But again, a lot of variations between them. And then the same is true for the liquid storage. And in this case, you just have very, very high liquid freshwater storage in the CAN ESM model. So one thing to kind of note about, again, these spreads that you do need to think about when you're kind of comparing across models is that they do have different numbers of ensemble members. So this can lead to some of the variations in the spread. And then also that the Arctic Ocean volume is not the same across models. So sort of when you're adding up this sort of freshwater in each of these cases, especially for the ocean, the actual volume of the Arctic in each of these models can sort of actually lead to some of the changes that you see here. And it doesn't lead to all of them though. Arctic Ocean volume maybe amounts to something like at most a 10% difference between these values. And so we have much stronger variations between them. But again, always something to kind of keep in mind when you think about this. So we can also look at then what happens to storage in the future. So what I have here are basically the sort of main takeaway from this is that future solid freshwater storage declines while the liquid freshwater storage increases. So what I have on the left here is freshwater storage again. You have solid on the top and the liquid on the bottom. And this is the ensemble mean freshwater storage. But this is kind of how basically bar plots showing how that changes with each of these future forcing scenarios relative to the historical. So historical is 1980 to 2000. It's always in gray. And then the SSPs are 2080 to 2100 averages. SSP 1-2.6 is always going to be in this navy color. 5-8.5 is always going to be in the goldenrod. And I try to adhere to that as much as possible throughout this talk. And then the error bars are basically a plus or minus 1 standard deviation of the ensemble members around that ensemble mean. And so what you see from this across the board is that the solid freshwater storage declines in the future. Pretty majorly. It's stronger for SSP 5-8.5 across these models than it is for SSP 1-2.6, which is pretty, makes a lot of sense given the higher radiative forcing. But at the same time, then the liquid freshwater storage increases. And so that is in part due to melting sea ice, though, but it's not all of it. So it's not just that the sea ice changes account for all of the changes they see in the freshwater. And again, be a little careful here because these axes are quite different in terms of scale. But again, what you see is that typically you have larger changes in freshwater storage or increases in freshwater storage for SSP 5-8.5 and that goldenrod color compared to SSP 1-2.6. And this is sort of the same across all of these models in terms of what is going to happen in the future. Now, of course, the magnitude of those changes varies pretty strongly across the models. So you're not seeing a very strong agreement in terms, again, of what the magnitude is, but in terms of what the sort of sign and the trends in those changes, they all tend to agree. Now, you can kind of also look at this over time to kind of get an idea of what this, how this actually happens. So now what I'm showing you is the multimodel mean freshwater storage over time. So solid on the top and liquid on the bottom, historical in gray, SSP 1-2.6 in navy, and 5-8.5 in the goldenrod color here. And largely what you get from this, again, is that sort of you see this very strong declines in the solid storage that tend to sort of, for SSP 5-8.5 are largely kind of going to 0 here, and 1-2.6 kind of leveling out at a pretty sad value, but something subtly higher, and then strong increases in the liquid storage. Now, when I'm taking the multimodel mean here, I'm taking the mean of the ensemble means. So I do the ensemble means for each of the 7 models, and then I take the mean of those 7 models to get this multimodel mean. So that way you're not weighting too heavily the models that have more ensemble members. And the envelopes here are not 95% confidence intervals. They actually just show the maximum or the minimum value of those that any of those 7 ensemble means achieves at any given time. And so this is kind of to be the most sort of stringent boundaries in terms of the changes between these two scenarios. So there are actually differences in the scenarios for the sea ice at the end of the solid storage at the end of the 21st century, but not at least major differences for the liquid storage. Now you can also look at the historical solid freshwater fluxes. So we're going back to our box and whisker plots. This is now solid fluxes through these 6 different straits. Here's our handy dandy map. Sign convention is always positive is into the Arctic, a negative value is out of the Arctic. So here's 7 different models here. In this case, we have our vertical dashed lines, which are once again observations. And then the gray bars, these sort of gray filled areas, are plus or minus the error quoted on those observations if they existed or if they were provided. These are mostly from Hain et al. Again, this is 1980 to 2000 because we're looking at the historical period. And these are sort of the spreads across the models. The zero line here is in this solid thin gray line. So if you look at the sort of spreads across these models, basically, once again, what you're seeing is there's pretty major differences in terms of how, of what the values are in these fluxes and in terms of how many of these models actually are comparable to observations. So you've got some models, for example, in the Bering Strait coming kind of close, but sometimes they don't even agree on the sign of those changes. Same says case sort of for the Nares Strait, but in any of these though, for the most part, not more than most models don't come close to observations for more than 2 of the straits in terms of the solid fluxes, and then in some cases like the Davis Strait, you actually have sort of all of the models are biased sort of in one direction. So again, a lot of sort of different changes within these models. So a lot of different things kind of going on here. Now, again, you can also look at the future changes in the solid freshwater fluxes, and much like what happened in for the case of the solid storage, you see future declines in solid freshwater fluxes. And that's not really surprising because your ice is going away. So there's nothing really to flux out of most of these passageways anymore. So now what I'm showing you is, again, we're going back to those bar graphs here where you've got the historical period in gray, 1980 to 2000 averages, and then the SSPs, 2080 to 2100. And so those are sort of the changes over that period. And largely what you see is just major declines in the solid freshwater fluxes through all of these straits, and that are typically larger for SSP 5-8.5 than they are for SSP 1-2.6. And so the ice, in some sense, is a fairly straightforward story. Do note that in these cases, the axis values are quite different. So when you're comparing across straits, just keep that in mind. But again, what you also see is when you're comparing across all these different models, their magnitudes are quite different over the historical period, and then also in terms of the future fluxes. So you can then also look at sort of the time series of those changes. This is now multimodel mean solid freshwater fluxes through these 6 different straits over time. And again, they more or less show you sort of the evolution of what the bar graph showed you previously, which you've got these sort of changes in fluxes that they're all just kind of trending towards 0 over time as you decrease the sea ice within the Arctic Ocean. And that for the most part, there are differences, but there's visible difference between the 2 scenarios, but for the most part, they don't actually sort of fall outside of each other's envelopes, except maybe in Franz Strait and then the Davis Strait toward the end of the 21st century here. So again, major declines in sea ice seem to be what's in store for our future, at least according to these CMIP models. You can look at liquid fluxes too. So we're going to go back to the historical period now and look at the liquid fluxes through these straits, the ocean fluxes. Once again, you've got observations in that magenta dashed line. The gray are that plus or minus, the error on those observations when they exist. And then these are the fluxes themselves, and these are the spread in those fluxes based on the ensemble members in each model, which are the box and whiskers. So once again, you're seeing pretty major differences in terms of the means and the spreads in the models. But to some degree, they're actually a little bit better at getting the liquid fluxes compared to how they did for the solid fluxes. And so most of them are a little bit closer to observations. And then in this case, for example, for IPSL CM6A, you actually have this model being, within the range of observations, or at least some of its ensemble members are, for 5, I think, of these 6 straits here across the models. So generally a little bit closer agreement, but again, a lot of differences in magnitude, size of these fluxes, and then in some cases like Barrow Strait, all of the models just kind of underestimate this flux. You can also look at the future liquid flux changes. And so these future liquid fluxes are really just showing an increase in freshwater export, except of course the Bering Strait and the Barents Sea opening. So Again, this story is maybe not as obvious as the sea ice story here, but for the most part, what you're getting is just a sort of increase in export. Do know again that the sort of scales of these axes are slightly different. At least they're the same order of magnitude in these cases. But again, the numbers are quite different. But what you get for the most part is that in SSP 5-8.5, the changes are typically stronger than SSP 1-2.6, but not always. There are certain cases and in certain straits where one model kind of shows some sort of different behaviors in terms of what is happening in the fluxes in those straits. So they don't always agree 100% on what is happening. But largely what you're getting is an increase in export from the Nares, Fram, Davis, and Barrow Straits. And the Bering Strait, though, everything kind of remains much more stable. You've got places and models basically which are saying that there's really not that much difference between 1-2.6 and 5-8.5. And that they're really not that much different from the historical period, even though there are changes and the magnitudes of these models are quite different. For example, Myrock just has very, very low freshwater transport through the Bering Strait. Another interesting behavior is what is happening in the Barents Sea. You're getting this sign change in the freshwater fluxes. So in the historical period, you are sort of a weakly negative export, and that's turned into a very strongly positive import into the Arctic over this period. And so to kind of understand these changes, though, it's really helpful, and I'll talk about this in a second. I just want to get through these time periods first here. We can look again at the multimodeling liquid freshwater flux again over that time period. And again, these are largely kind of showing you what we've seen before. The Bering Strait liquid freshwater export is actually largely stable pretty much over that entire 1980 to 2100 period. There are some changes in the Narrows, Barrow, and Fram Straits. And then in the Barents Sea, you're seeing this sort of change from this sort of negative value of the flux to something relatively positive by the end of the 21st century. And that's actually quite different between SSP 1-2.6 and 5-8.5. So again, a lot of things are happening here. But again, if you want to understand what's happening here, it's really helpful to kind of go back to sort of definitions of our fluxes. So if we want to know why the Barents Sea liquid flux changes sign in the future, for example, or why the Bering Strait is stable, it's helpful to kind of look at our volume fluxes or a definition of our volume fluxes in and out of the Arctic. So if you look at this, you've got two terms here. You've got the salinity term, which can be positive or negative, and you've got this velocity term, which can be positive or negative. And basically what that means is that there's two ways in which you can get an import into the Arctic, and there's two ways in which you can get an export from the Arctic. So you can have negative salinity, positive velocity, that'll give you a negative sign. And then you could have positive salinity term and negative velocity term, that'll give you a negative sign again. Or they can both be positive or both be negative, leading to a positive sign change. And so it's really helpful then to sort of break down these fluxes in terms of what is an anomalous salinity contribution and what is a velocity or a volume contribution, because those two things don't necessarily have to vary together. So what I do is I just decompose those fluxes to get their separate time varying salinity and volume contributions. So what I do is I just say the salinity is some mean salinity S bar plus this time varying component S prime, the same thing for the velocity components. And these means are always going to be the 2080 to 2000 to 2100 mean. And the anomalies are going to be relative to that. So I'm not going to go through the math, but basically the terms that I'm trying to understand here are this S bar U prime and this U bar S prime term here to kind of understand what's the salinity contribution and the velocity or volume contributions. So if we go back to our liquid freshwater flux time series, this is the ocean, again, the ocean freshwater fluxes through these various straits here. That's what I have on the left, so going back to that. And now what I have on the right is the multimodel mean liquid freshwater flux decomposition. And so what I'm showing is sort of the volume contributions, which are always going to be in purple, and the salinity contributions to those fluxes, which are always going to be in green. The darker colors are always SSP 1-2.6, and then the lighter colors are SSP 5-8.5. And what you kind of see from this then to kind of orient yourself, these are freshwater flux anomalies now, so they're always relative to whatever the mean is in each of these straits. What you can kind of see here for Bering Strait, though, is that you've got these sort of freshwater anomalies over time. The salinity anomalies actually act to freshen the Bering Sea inflow, the Bering Strait inflow. while the volume contributions actually act to slow it down. So together, though, these are basically compensating errors, though, in terms of what they're doing to the freshwater transport. And because of that, what that does is it leads to this relatively stable Bering Strait inflow over that period. Now, Fram Strait, in this case, everything, the anomalies are always sort of acting in the same direction to sort of reinforce what is happening here. Whatever is happening in the Fram Strait, whether it's sort of an increase or a decrease in these fluxes. And then we can go to the Barents Sea. And the Barents Sea is a really interesting one where we're like, okay, how do these things change sign? Well, if you look at the Barents Sea, basically what it's saying is that the volume contributions, these purple lines are relatively small in terms of what is happening in driving these changes or these increases that you see in the freshwater import. And then it actually is all coming down to these salinity changes. So you're actually getting a freshening of the waters that are then entering the Barents Sea. And that is largely what is just sort of driving the changes in this region. So you didn't get a change in sign of the transport. It's not like your current reverse direction or anything like that. Basically what happened was you just made the waters fresher. And then that is actually leading then overall to a change in the sign of the freshwater flux itself. So there's actually quite a lot of information within these plots, and you kind of need to sit with them for a much longer time than we have in this talk. But I'm happy to kind of chat more about those. So I'm just going to kind of conclude here real quickly. So largely what we saw here is our freshwater storage and our fluxes over the historical period vary widely across models. Few are consistently close to observations. In the future scenarios, all of these models exhibit strong declines in solid storage and fluxes as the Arctic sea ice coverage declines. And then liquid storage and export generally increase in the future in all the models. But of course, exceptions to this are then the Bering Strait, which remains relatively stable, and then the Barents Sea opening, which actually reverses sign due to salinity changes. And of course, the magnitude of all of those changes are still highly model dependent, but at least for the most part, they kind of agree on sort of the basic idea of what's going to happen in the future. And all of these things suggest an acceleration of the freshwater cycle and a dynamically different Arctic by the end of the 21st century. So that's all I have for you. And I think I'll open it up to questions.
Great, thanks very much, Hannah. Thanks for that. Important results coming out of CMIP6. Definitely interesting to look at changes in the Arctic. We did have a question. Well, first of all, if you have a question for Hannah, feel free to use the raise the hand feature in the participants window or type your question in the chat. We did have a question come in during the talk from Aishu, so I'll read that out here. So he says, nice talk. Wondering why not use the control run mean salinity from each model as the reference salinity, since by doing so, one can take the model bias out.
Yeah, we thought about that. And I think in this case, I just want to make all of the models comparable to each other. And so, yes, it doesn't take out the model biases, but if you're not referencing the same salinity across everything and comparing it to observations, it just makes everything hairier in terms of an intermodel comparison. So yeah, the reference salinity is a really tricky beast, but we kind of just chose to do it this way for consistency purposes.
Cool. So next, Gokhan has a question. Go ahead, Gokhan.
Yeah, I mean, it is related to essentially your number 1 and number 4 bullet here in the conclusions.
Mm-hmm.
You are showing quite a bit of, let's say, inconsistency or change among the models under the same, let's say, forcing conditions, or it doesn't really matter what the conditions are. Have you looked at a process level, how these differences come about? In other words, what are the responsible mechanisms at the process level that primarily contribute to the differences among the models? And perhaps another way of asking that question, how are the variabilities or responses correlating, or are they dependent to model biases, and in what way?
Yeah, so at the process level, I didn't really look at like what are the physical mechanisms driving these like exact changes within the models, because I feel like that's 7 different studies waiting to happen. But in terms of the sort of magnitude of the changes in terms of internal variability, typically what you see in these let me see if I can, oh no, that was the wrong one. Okay, let me see if I can go back to some of these sort of box and whisker plots. We'll just pick this one, for example. What you typically see is the sort of the spread, the sort of differences in the model means themselves are actually larger than the spread within an individual model. And so to me, what that's saying is that these differences aren't really driven by internal variability, or at least not internal variability alone. And then in terms of some of the other variations, I think a lot of them, I don't know, yeah, I can't speak necessarily to what the processes are that are leading to these different variations, but for something like this, for example, going back to the sea ice concentration, we know, and really I should be looking at sea ice thickness here if we're really talking about storage, because that's directly related to the volume. We know that there are biases in that, and that is definitely going to lead to some of the variations within these models. So biases in the sea ice state are definitely going to matter in terms of like the storage, but also ocean biases. So how fresh or saline your ocean is. And that's kind of what you see here in the freshwater storage in Canny SM5, where you end up having an incredibly fresh model, and that actually ends up leading to this very, very high values of freshwater storage as compared to some of these other things. So it's wrapped up in biases, but I don't, I can't speak then to how much of it is wrapped up in actual like differences in, say, like how, sort of the Arctic atmosphere compares across the models, and how that then leads to sort of, say, Arctic ice and ocean circulation changes, or at the level of what's happening into these individual straits, like how truly biased they are, at least in terms of anything other than their sort of salinity or their velocity. From previous papers, I know that Alex did, volume changes tend to do a little bit better in the straits in terms of their volume transports. It usually is salinity biases, but again, I haven't looked in too much detail in these models as far as to what's driving that. So I hope that's kind of my broad brush explanation of what's going on here. But individual processes is kind of a beastly but very interesting thing to think about.
Okay, thank you very much.
I see Dave Bailey has a question. Go ahead, Dave.
Yeah, nice talk, Hannah.
Thank you.
So I guess I have sort of a two-parter, but I mean, I might have missed where you said what the reference salinity you were using for the sea ice for the solid fluxes, and I mean, is that sort of
everything's 34.8?
Yeah. Okay. Oh, yeah. Well, that's the ocean, but what about
also the solid fluxes? Yeah, the relative.
But for the sea ice itself, is it 4? Is it?
Oh, you mean like what is there? Okay, so it differs across models. So it's somewhere between 4 and 6 usually.
Okay.
But you still reference it to 34.8, so you can put it on the same scale as the liquid ocean ones.
Okay.
Yeah.
Okay.
Mm-hmm. And then you kind of convert that into a liquid volume, actually. So that you convert the solid storage into that. Yeah. So you actually do a density conversion.
Okay. Okay. And then in the solid fluxes, are you taking into account the snow on top of the sea ice? Okay.
Yes, if it's there and they give me that. But yeah, for the most part, they do provide that. So the snow is included in that. Yes.
Okay, thanks.
Mm-hmm.
Any other questions? I did have a question maybe relating to Gokhan's question, but just thinking about those differences in the spatial extent of, I think it was freshwater changes, the 2 different models that you showed that had very different like spatial extents. Yeah, this one. And, do you think that higher resolution simulations could help to isolate some of those changes and why we're seeing those different spatial patterns in different models?
I would imagine yes. I mean, they certainly impact the fluxes, especially through the Canadian Arctic archipelago. It's going to impact circulation, especially because you are dealing with also higher resolution models typically are better at, resolving eddies. I should be a little careful here though, because in the Arctic, your deformation radius is incredibly small. But they do, I think, in at least some of these studies typically tend to do a little bit of that better. And so I imagine that will sort of lead to circulation changes. I personally, again, haven't looked at a high resolution model in terms of what they do in the Arctic, but I do know that leads to some improvements. It would also be interesting interesting to kind of see what happens then with the Barents Sea sea ice biases. I've seen, I think, and I've had a few discussions with Mitch Bushhook about this, where this could sort of be related to sort of the eddy heat fluxes into the Arctic, and how that might change then impact the actual sea ice formation in that region. But I don't know that it necessarily solves all of the problems. So resolution helps, but again, it's not our panacea that's just like, here, there's no more biases. You know, there's probably also, you know, atmospheric circulation biases, things like that, that like I haven't even begun to dig into, you know, how they handle their riverine inputs, what's happening in Greenland. So it's kind of an open-ended thing. And my hope is that, yes, that will improve some of it. But it's going to be kind of coming down to, yeah, individual model physics, I think, too. So
Cool. Well, thanks very much, Hannah, for a great talk.
Thank you.
We'll close it out. And so next week we have Darren Waugh from Johns Hopkins University presenting. So hope to see many of you then. And yeah, thanks again, Hannah.
Awesome. Thank you, everyone. I appreciate it.